In this video, we'll talk about a few important concepts for evaluating limits and apply them in a few practice problems. Let's get started. First off, we want to cover some important concepts that'll be useful for the problems we're about to solve. If we have a function that's continuous, like g of x, then we know the limit of g of x as x approaches a, or any number, is equal to g evaluated at a, or at that number. And this is really useful because it makes limits easier to evaluate if we know a function is continuous. For example, we know all polynomials are continuous, so we can directly evaluate any polynomial to take the limit approaching a certain value, and we can extend this to any function that doesn't have a break or a hole. Many sections of individual functions are continuous, even if the whole function isn't continuous. If we want to take a limit at a spot that isn't continuous though, we have to consider the following definition. If the limit from the left of f of x and the limit from the right of f of x are equal, then we say that the limit without a direction does exist and it's also equal to the same value. So here's the definitions that we'll be using. Let's jump into some problems. For our first example, we're given the equation and graph of a piecewise function f of x and are asked to find the limit of f of x as x approaches 1. For practice, let's evaluate this limit using first the equation and then the graph. But before we start this together, pause the video and try it on your own. To use the equation, we need to find which of these intervals apply when x is near 1. In this case, 1 is well within the interval from -1 to 2, so the only segment of the function pertinent to this limit is the parabola f of x is equal to x squared. And we can say that the limit of f of x as x approaches 1 is equal to the limit of x squared as x approaches 1. Remember the definition of continuous functions? Because x squared is a polynomial, and all polynomials are continuous. So we can apply the definition of continuousness, and know that the limit of x squared as x approaches 1 is equal to 1 squared, which in this case means the limit is equal to 1. Looking now at the graph instead, we can observe that near x equals 1, the graph doesn't have any holes or transitions or breaks in segments. Remember that if a function doesn't have breaks or holes, it's continuous. So we can say f of x is continuous so long as we don't look too far away from x equals 1. Because this part of f of x is continuous, and the graph passes through the point 1, 1, we know the limit of f of x as x approaches 1 must be equal to 1. Here's a quick summary of the two ways we found this limit and how they compare. Notice how both methods leverage the fact that f of x is continuous near x equals 1. Feel free to pause the video if you want to look at it more. Next, we're asked to find the limit of f of x as x approaches -1. We'll solve this using both the graph and the equation, like before, but this time we'll start with the graph. Again, I definitely recommend you pause the video now and try this yourself before watching more of the video. Unlike the previous problem, the point where x equals -1 is a transition from one segment to another in the graph. Because f of x is broken up into segments around x equals -1, we don't know if f of x is continuous at -1. In this case, we must consider the limits as f of x approaches -1 from the left and from the right individually. Remember, if the left and right limit are equal to each other, then the limit exists and is equal to them. Otherwise, the limit doesn't exist. In this case, from the left, the function is a line that ends at the point -1, 1, and from the right, the function is a parabola, which ends also at the point -1, 1. Because both segments end at the same point, the limit from the left and the limit from the right are the same, and we conclude that the limit of f of x as x approaches -1 is equal to 1. Now let's evaluate the same limit using the equation representation. If you didn't pause to try this earlier, now's your second chance. We first look for which interval or intervals apply when x is near -1. In this case, 3 of them do. But because the value of a limit does not depend on the actual value of the function at the given point, we can ignore the point where x equals -1. This leaves us with f of x is equal to x plus 2 when x is less than -1, so from the left, and f of x equals x squared when x is greater than -1, from the right. If both of these functions approach the same value as x approaches -1 from their respective sides, then the limit exists and is the same value. Both x plus 2 and x squared are polynomials, and as such, are continuous, so their limits as x approaches -1 are equal to them evaluated at -1. Evaluating these functions yields -1 plus 2, which is equal to 1, and -1 squared, which also equals 1. Because both the left and right segments approach 1, the value of the limit is 1. Here's another summary slide of how we found the limit in both ways. Importantly, we got the same answer to both limits, and I hope you can see how we used the same tactics to solve the problem, regardless of whether we used the graph or the equation. Again, feel free to pause the video and think about it, or rewind if that connection isn't clear yet. The final part of this example asks us to find the limit of f of x as x approaches 2. We'll start with the equation, but first, pause the video and try it on your own. Similar to the previous problem, when evaluating this limit using the equation for f of x, the point we're considering lies between two intervals of the piecewise function. Now, the parabola x squared corresponds to the values of x less than 2 from the left, and the line -x plus 2 corresponds to values of x greater than 2 from the right. This means that the left limit of f of x is the limit of x squared as x approaches 2 from the left, and that the right limit of f of x is the limit of -x plus 2 as x approaches 2 from the right. Because these are both limits of polynomials, and we know that polynomials are continuous, we apply the definition of continuity one more time to find the limit of x squared as x approaches 2 from the left is equal to 4, and the limit of -x plus 2 as x approaches 2 from the right is equal to 0. Because the left limit is 4 and the right limit is 0, the two sides do not approach the same value, and we conclude the limit of f of x as x approaches 2 does not exist. Finally, let's evaluate this limit with the graph too. The left and right sides of the graph around x equals 2 are very disconnected. The parabola from the left ends at the point 2,4, whereas the line segment from the right ends at the point 2,0. Because the left side of 2 approaches a y value of 4, and the right side approaches a y value of 0, the left and right limits are not equal, so the limit of f of x as x approaches 2 does not exist, and we write d and e. Here's one final summary of how we evaluated this limit with the equation and graph. I want to point out again that even though the graph and the equation are very different notations of f of x, the underlying process for evaluating the limit is almost exactly the same. If these or any other concepts require some more of your attention, feel free to watch this video again. Reach out to your professor, recitation leader, or utilize the free tutoring services offered at the Aggie Math Learning Center. We hope this video was helpful, and remember that help is here if you need it.